Hello students, welcome to another lesson of project management, the fourth lesson, project scheduling. In this, the objectives of this lesson are to enable the students to understand work breakdown structure for a project, comprehend scheduling of project, illustrate how to use work breakdown structure for project schedule, and depict the project cost schedule. In the previous lesson, we have seen the log frame matrix. After the log frame matrix is done, the planning phase is continued by preparing an activity schedule. An activity schedule is a method of presenting the activities of a project which identifies their logical sequence and any dependencies that exist between activities. Thereafter, the resource scheduling is done. Activity scheduling is prepared in the following manner. First, main activities from log frame are listed out. Activities are fragmented into manageable tasks. Then clarify the sequence and dependencies of the activities and tasks. Resource scheduling is prepared by estimating the schedule and cost of each activity, task and subtask. Then assign expertise and resources to the activities. Now, let us understand the meaning of work breakdown structure. The abbreviation is WBS. Work breakdown structure is one of the foundations for project planning. A complex project is broken into manageable components in a hierarchical structure determining the activities needed to achieve the project objectives. This framework is considered as work breakdown structure or WBS. The work breakdown structure visually defines the scope of the project that a project team can understand. It provides help in activity and resource scheduling within timelines and also to have communication and control over the project. Nowadays, we have multiple software tools available in the market for developing WBS and also other schedules. The most common tool is Microsoft Project. What is not work breakdown structure? Work breakdown structure is about the decomposition of work or the task to be done, but not the roles of the people and the skill set required or the schedule estimations. It is just the identification of the task, but not its sequencing. What are the uses of work breakdown structure? Using WBS, the resource allocation, individual responsibilities, cost and time estimations are determined. It helps in quick calculation of overall budget as well as departmental budget. It also helps to identify potential risks. When a project is falling behind, referring the work breakdown structure will quickly identify the major deliverables impacted by the failing work package or late sub-deliverables. Easy communication at every level is possible through work breakdown structure. Hence, the overall project can be monitored and controlled at every level. The rules for developing WBS are: the main skill is to know at what level to stop the decomposition. Stop breaking down at the level where you can estimate the accuracy. WBS does not have to be symmetrical, that is, all paths do not have to go down to the same level. WBS need not have to bother about sequence of activities. There are two formats to represent WBS: tree diagram or graphical format, and the second is tabular diagram. You can see here in the picture, the first one, tree diagram. The main project name is taken as the main level, which is divided into activities. We see 3 activities in the diagram and they are indexed as 1, 2, 3. The next level is called task. Each activity is again broken down into tasks and they are indexed as 1.1 or 1.1. 1.2, and the second activity is divided into 2 tasks and the third activity is divided into 2 tasks. These tasks are again subdivided and they are called as subtasks. It is all just about breaking of the main project into different levels of subtasks. The next format is tabular form, that is, it is represented in the form of a table. The project name comes to the left, then the tasks are divided. Here in the picture you can see task 1 and task 2, and which are again divided into subtasks, which are again divided into work packages. Here is a simple example of WBS, the car manufacturing. The car parts are divided into many tasks: engine, interior, controls and chassis. Engine is again subdivided into cylinders, camshaft, alternator, piston. Similarly, for interiors, seats, controls, accelerator, brake, steering. You can see that all the branches, that is all the parts, all the levels are not equally divided. All these are important when we are considering a WBS. Now that the WBS is available, it is used to develop the schedule to attain project objectives within the time frame and estimated costs. Starting and end dates of each activity are clearly stated. Developing a schedule can be done by certain networking techniques. They are critical path method CPM, which is developed by DuPont. Second, PERT, program evaluation and review technique, developed by US Navy. And third, Gantt chart, developed by Henry Gantt. CPM and PERT are used to determine the shortest possible time for the project completion. In the case of CPM, it is assumed the details about these inputs are known with certainty, that is deterministic activity duration, whereas for PERT these details are not known with certainty, that is probabilistic activity duration are considered. Both approaches use a network representation to display the relationships between project activities. Gantt chart is a bar chart of the graphical representation of the project schedule. These techniques are dependent on identifying the activities and the sequencing of those activities. These network activities contain certain network terms such as activity. Activity is any operation which needs some resources like money, material or men for completion in a specified time. Activity is a definite part of the total undertaking. It must be accomplished in order to complete the project. Activity will be represented by an arrow. The length of arrow has no significance. The head of an arrow indicates the successor activity or the activities. The tail indicates the predecessor activity or the activities. Every activity lies between these events. Dummy activity. It indicates the logical relationship between activities, preceding and succeeding activity relationships, and does not require any resources like money, material or time. It is usually represented by a broken dashed arrow. Next is event. Beginning and end points of activity is denoted as event. Event is usually denoted by a circle which is divided into two equal halves. One half is meant for event number. The other half is further divided into two segments representing the earliest starting time and the latest starting time. This can be represented as shown in the figure here. Earliest start time. It is the time at which the activity commences and cannot be started earlier than this time. Earliest finish time. It is the earliest possible time an activity can be completed without interfering with the completion of any of the preceding activities. Latest start time. It is the latest time to start an activity without delaying the end of the project. Latest finish time. It is the earliest possible time an activity can be completed without delaying the end of the project. Next, critical activities. These are activities which fall on the critical path. These activities have 0 slack period. Critical event. These are events which fall on the critical path. Every critical event will have the same values of EST, that is the earliest start time, and LST, latest start time. Now, critical path. Critical path is the longest path of activities for completing the project. The total time required for the critical path is the shortest period of the project. All critical activities and critical events lie on this path. There is no slack time on this path. It may be represented by heavy lines or double lines or 2 strokes on the arrow. Next is slack. It is the spare time available for commencing an activity or spare time available after completing an activity. It is similar to float in CPM. That is, in CPM it is called float, in PERT it is called as slack. At times it used vice versa. Activity slack or activity float. It is the slack or float associated with an activity. It is computed by using the following formula, that is, activity slack is LST minus EST or LFT minus EFT, latest start time minus early start time or latest finish time minus earliest finish time. There are 3 types of floats: total float, free float, interfering float. Total float is calculated as LST minus EST, that is latest start date minus earliest start date. It is without affecting project completion. Free float, it is calculating earliest start date of next activity minus latest end date of previous activity. It is without affecting the next activity. The next is interfering float, that is total float minus free float. Next is node. The node is represented in the following manner, that is as shown in the picture. To the left you see EST and LST, and to the right EFT and LFT. EST is earliest start time, LST latest start time, and the activity is represented as a symbol or by a name. The activity duration is represented numerically. To the right we have earliest finish time and latest finish time. CPM has 2 calculations, forward pass and backward pass. Forward pass is a procedure in which EST values are computed. It starts with the first event and ends with the last event of the project. In this, the rule is EST rule, where all immediate predecessors must be done before any activity can begin. If only one immediate predecessor, then EST is equal to EFT of predecessor. If there are more than one immediate predecessors, then EST is calculated by maximum of all predecessor EFTs, and the EFT rule for forward pass is EFT is obtained as EST plus activity time. The backward pass. The backward pass is a procedure in which LST values are computed. It starts with the last event and ends with the first event of the project. LFT rule is calculated as if activity is the immediate predecessor to only one activity, then LFT is obtained as LST of immediate successors. If activity is the immediate predecessor to multiple activities, then LFT is obtained as minimum of LST of all immediate successes, and the LST rule is LST is obtained by calculating LFT minus activity time. The next term is activity table. This is the table developed after breaking the project into small specific components called activities. In this table activities, their symbols, time requirement for each activity and their logical relationships, that is the preceding and succeeding activity relationships are arranged systematically. This is a basic step for preparing the network. The entire network technique is based on this activity table. Next is crash time. This is the time in which the activity will be taken up on crash basis for accomplishing. It indicates the shortest time for accomplishing the activity, but money is not the criteria here. Normal time. This is the time required when activities are performed in a normal way. It is usually the longest time for the project. Normal cost. The cost involved when activity is performed in a normal way and it is the least expensive. Crash cost. The cost involved when activity is performed on crash basis without consideration of the costs involved. Time saving is the main criteria here. Cost slope. Cost slope is obtained by a formula, that is CS, that is cost slope equal to crash cost minus normal cost by normal time minus crash time. Scheduling the project duration. Using an example, let us see how to schedule the project with deterministic activity durations and probabilistic activity durations. First, let us discuss scheduling the project with deterministic activity duration. Let us consider the following example to conduct CPM, that is the critical path method. We have discussed before that CPM is the technique where the deterministic activity durations are considered. Hence, here is an activity table of the project to install an air filter system in the chimney along with immediate predecessors and time estimates. This is the activity table where you can see A to H activities. In the table we can see the activity, their description, their immediate predecessors and the time taken. The time is demonstrated in weeks. The first one is building internal components is taken as activity A. Since this is the starting, we do not have immediate predecessors and the time is given for 2 weeks. Activity B, it is to modify roof and floor. Here again we do not have the immediate predecessor, but we have the time for 3 weeks. Next is C. Activity C is to construct collection stack, and for it the immediate predecessor is A and the time is 2 weeks. Next is D, to pour concrete and install frame. The activity before it is B and time given is 4 weeks. Next is E, to build high temperature burner. Previous activity is C and the time given is 4 weeks. Next is F, to install control system, where the previous activity is C and the time allotted for it is 3 weeks. The next is G, to install air pollution device, and the previous activities before G are D and E and the time given for it is 5 weeks. The last is H. Activity H is to inspect and test. The immediate predecessors, that is the previous activities before H, are F and G and the time given for it is 2 weeks. So, the total time to be completed for this will take up to 25 weeks. You can see all this representation in the form of a table, which is called the activity table. This table can be represented as activity on node network, that is AON, where activity is represented as node and arrow is represented as immediate predecessors activities in the following manner. Using CPM method, the forward pass calculation can be obtained as follows, which is represented diagrammatically as follows. Here in the picture you can see the calculations of EST and EFT. Here in the diagram you can see that in the first node we have 0 slack. Then for the activity A we have 2 weeks time and EST of A is 0 and EFT of A is calculated as EST of A plus 2 weeks, and similarly for B, C, D, E, F and H you can see the EST and EFTs. They are calculated based on the rules that are followed by the forward pass calculations. Next is backward pass calculations, where we obtain the LST and LFTs only. Now, the backward pass calculation is calculated from the end to the starting of the activities. First, the last one, for the H activity, LFT is equal to EFT of project. So, it is 13 as EST, 15 as EFT. Hence, we get 13 as LST and 15 as LFT. Next, we get F and G. Next, C, E, D, next A, B and the first node are calculated in the similar manner based on the rules that we follow for backward pass calculation. Now that we have obtained all the calculations, it can be represented in the form of an activity table again. Here we can see the project schedule and the slack times that are obtained through this. Hence, we get the critical path and slack times in the following manner, which is shown diagrammatically. In the diagram, the lines, the arrows which are depicted in blue color is the critical path and the time duration for it is calculated as the critical path duration. Next is scheduling the project with probabilistic activity duration. Previously, we have known the durations with certain, but now it is uncertain. Hence, they are called probabilistic activity duration. The CPM approach assumes that the duration of activities are known with certainty and the actual duration will turn out to be exactly as estimated. However, in practice this is not always possible and many projects involve variability in activity times. Hence, PERT analysis is used for uncertain activity durations. It involves 3 types of time estimates for each activity. First, the optimistic duration, which is the time an activity will take under the most favorable conditions. Second, the pessimistic duration, which is the time an activity will take under the most unfavorable conditions. And the third is the most likely duration, the most realistic time an activity will require to be completed. That is the time an activity will take under normal condition. These estimates are used to calculate an expected activity time represented as T base E and variance for each activity based on the beta probability distribution. Expected activity time T is calculated as A plus 4m plus B by 6 and the variance is calculated as B minus A by 6 to the whole square and the standard deviation is the square root of variance. Using these formulas and the example that we have used previously for calculating the deterministic activity duration, we get the following table. Here in the table you can see that the optimistic times, most likely times, pessimistic times are given for each activity and hence the expected durations based on the formulas that we have just mentioned are given as well as the variance is given. From this table we calculate the project variance, the overall project variance as the sum of all variances of all critical path activities. What is the critical path? All those which had 0 slack. Previously in the calculation of CPM method we have determined the critical path. So, all those activities which are in the critical path, we calculate the variances of all those in this table. We take only those activities which fall on the critical path. Hence, ACEGH, that is 0.11 plus 0.11 plus 1 plus 1.78 plus 0.11 gives to 3.11, which is the project variance. Now that we have the variance, the standard deviation is the square root of it, which gives to 1.76. That is, if at all we want to calculate the probability of finishing the project within 16 weeks, let us have the PERT assumptions as project completion follows to normal probability distribution and activity times are independent. Hence, normal distribution parameters, that is the mean time is 15 weeks and the standard deviation is 1.76 weeks. Hence, from the mean time and standard deviation time, hence the normal probability equation is obtained by calculating target time minus expected time by the standard deviation, that comes to 0.57 weeks. That is, 16 weeks is 0.57 standard deviations above the mean of 15 weeks. That is, the probability is 0.7157 for the z value, that is the normal distribution time is obtained as 0.57. This is based on the normal table of probability. Hence, the normal curve is obtained as shown in the diagram here. That is 71.58% of probability is there to complete the project within 16 weeks. For the target of 99% probability, based on the normal table, we get the z value, that is the normal distribution value, to be 2.33. This is diagrammatically represented in the following manner. Hence, the target completion time, that is mean time, can be obtained as normal distribution value z is equal to x minus 15 by 1.7, that gives to 2.33. Hence, to complete the project for 99% of probability, it takes 19.1 weeks. The approach in this process involves determining the cost per week or month for each activity. Three basic steps are followed for this process. First is identify all costs associated with each of the activities, then add these costs together to get one estimated cost or budget for each activity. Second, convert the budgeted cost per activity into a cost per time period by assuming that the cost of completing an activity is spent at a uniform rate over time. Third, using the ESTs and LSTs, find out how much money should be spent during each week or month to finish the project by the date desired. Using the same example which we have used for calculating the durations, we can assume that the cost for each activity is spent at a linear rate over time and dividing the total budget for each activity by the expected time to get the weekly budget for each activity. For example, activity A, it has 2 weeks time. So, total budget cost is divided by expected time, which is equal to budgeted cost per week, that is 22,000 by 2, that gives to 11,000. For the remaining activities, you can see it in the table. As the third point states, using the ES and LS, we can calculate how much money should be spent during each week or month to finish the project by the date desired, and hence it can be computed more specifically. Hence, we can get the exact cost distributed per each week using ESTs in the following activity table. And similarly, using LSTs, we get the exact cost distributed each week, which is represented in the following table again. This is how the scheduling of the project is done. Any questions?
Ma'am, is WS part of scheduling of the project?
No, WBS is not part of the scheduling of the project. However, WBS is used as the source for preparing the schedule of the project. Using WBS, the sequencing is done and the activities are divided. For the activities, the sequencing of the activities is done, and then the techniques, that is the networking techniques, are applied and the schedule is prepared in a detailed manner. This is how the project scheduling is done and how the WBS is prepared and used for the project schedule. Thank you.